YOLO Composing Gloves here, and today we're going to be answering a static equilibrium problem, a problem that involves torque. So we have, suppose that you placed a 10-meter ladder, which weighs 100 newtons, against a frictionless wall at the angle of 30 degrees. And so frictionless wall is one of those words that can slip past you. So just remember the wall has no friction. What is the coefficient of friction between the ladder and the ground? So we want to know, so we're looking for, coefficient of friction between the ladder and the ground. There's none on the wall. And then we say, knowing that the ladder is in static equilibrium. And so we really quick call up our definition of static equilibrium. We say, well, in static equilibrium, there are two conditions. One is that there are no outside forces applied. Basically, no linear forces are being applied. It's a translational statement of equilibrium. So if basically no one's going to go up and push our ladder over, okay? It's in equilibrium in that way. And it's also got rotational equilibrium. So that either means it's rotating at uniform angular velocity or that it's just sitting there. In our case, it's just sitting there. And so our ladder is just sitting there. We also as we get into this, we notice that this looks like a triangle. So we're going to use a triangle. But we don't have a box or an object on this. So we're actually going to be drawing multiple points on our object. And this also means that because it's in equilibrium, we can actually put the point we want to call the fulcrum anywhere we want, because we're going to be using two diagrams. We're going to have one for forces and we're going to have one for torque. And in torque, we're going to have to define a pivot point. And with objects in equilibrium, you can put it wherever you want, but there's actually an advantage to putting it in some spots. And that's why we are given a length. We were said that the ladder is 10 meters long. That's why. Also, this is part of my notes. I'm going to only solve symbolically because that's like half the time that's what I have to do on my tests anyways. A lot of times numbers are given to us in the homework just so we can have some sort of an answer. So we say we just want to get the correct equations so that we could plug in the numbers if we so desired. So we say, okay, let's take a look at this. So we were given, what were we given? We're going to make our columns. So we're going to have a given column, a to be determined column, a free body diagram 1, and we're going to have multiple dots on our ladder again. So it's sort of unique. In my class, this was the first time we ran into this. And then we're also going to have a second free body diagram. So one free body diagram's just your standard draw the forces, resolve things. In this case, we actually don't even want to resolve anything. And the second one, we're going to be considering torque. And so we're going to be talking about how to set up that. And we're going to have two sets of equations because we have two diagrams. And then that's it. After that, you just solve. So half the battle is just setting the problem up correctly. So let's go ahead and take a look at our given column. We were given the length. That's 10 meters. We have the weight vector. That's 100 newtons. And instead of writing weight, I prefer mg. So we wrote mg. And then we have theta. And we're told that's 30 degrees. And we're told that the wall was frictionless, right? So we take note of that. Wall is frictionless. We want to know the coefficient of friction of the ground. So we have mu sub ground is equal to what? We don't know. It's going to be exciting, right? So we say, well, first let's do the thing that's really easy to work with. And that is our free body diagram number 1. And in this free body diagram, we're just going to do the forces. So we say, okay, I'll draw a triangle. So we draw this triangle, and this line right here, the hypotenuse, is our ladder. So there's our ladder. And torque, remember with rigid bodies, torque cares about the distribution of our matter, of our mass. It doesn't just care about the mass as a single point. It cares about how it was distributed. So we need to define a center of gravity. Now we're going to be really clever, and we're going to claim that our object is homogeneous. And basically that just puts the center of gravity right there, smack dab in the center of our ladder. So that's really convenient for us. We're going to use that later. But for now, that's where we're going to put our weight vector. So here's our weight vector. But this is going to have some more implications a little bit later. Now we notice that, well, I guess we should take care of a couple more housekeeping things. Make sure you include theta on your diagram. Don't want to get dinged for that one. And then let's go ahead and put down the normal forces. So there's actually two normal forces because we have two surfaces. We have the ground and we have the wall. So since our object's touching them both, there's going to be two, and they're going to be drawn at the points where they're touching. This is the first time we've had to do something like this, so it's kind of cool, I guess. We're going to draw it directly on our ladder, and we say, okay, the normal force is always perpendicular to the surface. So we draw two perpendicular forces. We have one coming off the wall and one coming off the ground. Now we are told there is a coefficient of friction, a force of friction on the ground. So we go ahead and draw that. And you notice that mine is pointed, from my perspective, it is pointed to the right. I'm not sure if this is different on the screen. So we have pointed to the right? Force of friction. How did I pick that? Well, you just have to ask yourself the question, what would the ladder be likely to do? And what direction of motion would it move if it could? And we say, well, there's friction on the ground, but there's none on the wall. So the chances are is the ladder is going to slide down the wall and push the ladder outward. And so the force of friction is opposite that direction of motion. So it's going to go inwards. So that's why the force of friction is pointed that direction. Also, all these like dashed lines here are just to show that these are surfaces. So, okay, and we pretty much got all our forces on there. It's not really that crazy. So we also wanted to find our positive directions real quick. So we have a positive going in the direction of motion, just because that seemed to be the easiest thing to do. Normally this is negative, in math, but in physics, we could say whatever we want as long as we define it correctly. And then we also have our positive going up, which makes sense usually. So, all right. So now we're going to move over to our free body diagram number 2. Now on this one, we have some resolving vectors. So this one is a diagram that deals with torque. We care about our torque, and we're going to use this because we actually cannot solve the problem completely using only the forces. We also need the torque to figure this out. So we say, okay, now remember with torque, we only care about perpendicular forces. So we don't need to worry about resolving all the vectors because we only care about the ones that are perpendicular. Any vectors that go along the direction that are at basically at 180 or an angle of 0, then that's not going to do anything. It's not going to do anything to our torque. So we only care about things that are perpendicular. So we're just going to half resolve vectors. So we say, all right, first, let's just draw our triangle. As you can see here, all the same stuff. We have our force of friction, our normal forces are here. And then we ask ourselves the question, like, how do we do this torque thing? Well, our object's at an angle, so let's put our x-axis, and this right here is my x-axis, this green line. And that's going to be what we consider the torque being applied to. And then we need to say, well, let's pick a fixed point. Because since this object's in equilibrium, we can actually pick any point on this object and it will work out. So we could pick this point right here. But in order for torque to work, we have to know the distance from, like, say here to there. And this could be you could do it, but it's just a lot more work. There's usually a point that is an ideal point to work with. It makes dealing with the distances easy. So this is where I bring back up the fact that we said that our object was homogeneous. This means that our center of gravity is in the middle. And that means that if the whole thing is a distance to L, just L, it's just L. That means that half the distance is L over 2. And the other half is L over 2. So this is a really convenient thing to sort of realize, because we can use this in our equations for our distances that we're concerned with. So that means that our pivot point should be a point on one of the ends. And it seems to make the most sense to put the pivot point or the fulcrum down here at the bottom. And we do that because we can use that 2L and L definition. And that's really easy to work with. So we put our fulcrum down here. And then we just have to resolve a couple vectors. So we say, okay, where are the forces perpendicular to this thing? Well, we don't need to worry about N1, since N1, we can actually get N1 from our first equation, because N1 will deal with the, we'll be able to solve it from the Y component of our first diagram. So N1 will be easy to find. Actually, the name of the game will be to find N2, as you'll find out. So we want to resolve N2, and we only want to resolve it to the perpendicular component. So we go ahead, we draw our altitude, which it's a little sloppy here, but there's the altitude. So we have a force like that, and that would resolve, if this is theta, this would actually become N2 sine theta. So nothing too crazy there, because this would be theta, And that means that we could move this over and use trig and all that stuff. I'm assuming you've got a handle on this. Also, we would do the same thing for the weight vector, right? Because that's going to create a perpendicular force. So we do that and we find mg cosine theta. And you can't really see it here, but I did mark this as theta. The little thing there is supposed to be a little marking of theta. And that's that. Now you notice I did redraw my y-axis for both of these. These are supposed to be parallel. And that's just so I could resolve my vectors. So vector resolution, nothing crazy there. So now that we've got this all done, let's go ahead and write up our equations. Now our equations are really easy. You just, first let's do the ones that we know all about, we're really comfortable with using. So that would be our force diagram. So we have a force, so we've got two dimensions, we've got x and y. And so we've got an F net x and an F net y. And since it's in equilibrium, they're both equal to 0, which is really nice. So then we ask ourselves, well, what forces are on the x-axis? And this is a little tricky. You might mess this up. I don't know. The N2 is on the x-axis. Even though it's like way up there at the top of the ladder, the N2 is an x vector. So we have to consider that. And then also the force of friction. So it's a little confusing because now our vectors aren't on the same level, but since they're applying to the same object, we consider them both. And so that would be, well, how do we define positive? We define positive going to the left. So we say, okay, that's going to be N2 minus our force of friction. And it's at F sub S, by the way, because it's static friction. Don't put a K, you'll lose points. So we say, great, okay. We have our force of friction. We were not given that, so we need to define it. And we say, well, in order to define our force of friction, remember that's just mu sub ground, because it's mu sub ground because our force of friction is on the ground. And then it cares about the normal force coming from that same point that the friction originates at. So we care about N1. Do not put N2. It has to be N1. So because it cares about that point that it originates at. So it's going to be mu sub ground N1. And then we say, okay. Now we can plug this in. So we had N2 minus our force of friction. And so now we've got N2 minus our mu sub ground times N1. And that's still equal to 0. So we say, okay, great. There's our equation. And then we say, okay, can we simplify this further? And we say, well, let's add m ground to both sides. So we just move it to the other side. And when we do that, we get m ground N1 equal to N2. Then we can divide by N1. When we divide by N1, we find out that m ground is equal to N2 over N1. And we're trying to find out m ground, but the problem with this definition is we were not given N1 or N2. So if we could not plug numbers in at this point. So in order to take this on, what we're going to do is we're going to go to our other axis, right? So we come back over here, we say, what about our y-axis? Can that help us out? So we say, well, on our y-axis, we define our axis on this one just to be like regular good old XY instead of a slanted deal, because we don't need to worry about resolving things to be perpendicular with our objects, if you're wondering about that. So we've got our weight vector here, mg. We say, oh, okay, well, that's up and down. And we've got our normal force. That's up and down. mg is negative. So our force is going to be N1 minus mg, right? And so let's go over here and check out our equation. So we have F net y equal to 0. We say, well, F net is N1 minus mg. And we say, well, N1 is simply mg. And so if we can, now that we know this, we can come over to our old equation and say, well, let's just replace N1. So now we've got mu sub ground is equal to N2 over mg. And so we actually know mg, but we don't know N2. So we're still stuck. So in order to do this, we say, well, there's no way to find N2 from any of this stuff without having two unknowns, because we don't know m ground or N2. This is where our torque definition comes into play. So we say, all right, let's go to our other diagram. Maybe we could figure it out from that. This is a little more complicated thinking, so this is why let's go as far as we can with the simple stuff. So we say, okay, we've already resolved all our vectors and stuff, so we come over to our equation and we say T net. So that's just that's tau net equal to 0. And now we got to say, well, what is the sum of the torques on our object? And now remember, torque is just equal to the distance, the lever arm, whatever you want to call it. And this is from the fulcrum. So times the force, the perpendicular force. That's supposed to be perpendicular. Perpendicular force times the distance that force is away from the fulcrum. So we defined our fulcrum right here. So our torque definition, that's our whole homogeneous deal. So we say, okay, well, this is pretty easy. We say, well, where are our perpendicular forces being applied? Now, this one we can ignore N1 because we already have N1, so we don't need to worry about it. And N1 is also at the fulcrum, so it's a fixed point anyways. Now, if we look over here, we say, and the reason why, so you might be still like a little hung up on this, that's because the distance to the fulcrum is 0. So it'd be N1 times 0, which is 0. That's why we can just ignore N1. So we look over here, we say, well, there are two other forces being applied at a perpendicular position or direction. So we say, okay, this mg cosine theta is, so let's figure that out. So we said this was homogeneous, so that means that this is the distance L over 2. And we have mg cosine theta times this distance, right? So we say, okay, mg cosine theta times L over 2. But we're not done. We have to figure out whether or not this is positive or negative torque. And this is where it's like, oh man, geez, I don't know. And so we ask ourselves the question, well, if we let this force do its job, which way would it push our object to rotate? And we say, well, our object would be pushed to rotate clockwise. If we let that force alone just act on this object, it would pull our object down, right? That's the direction it's going. So that means that our torque is going to be negative because clockwise torque is negative. Again, covered in my huge overview of my physics class. So we say, okay, mg cosine is negative times L over 2. And L over 2 is the distance, and we're going to multiply it, so it all becomes negative anyways. Then we look at our other torque, and we say our other torque is this N2 sine theta, this vector component of our normal force. That's pulling up, and so that just means that as it pulls up, we say, well, our object will be likely to rotate this way. And since it's likely to rotate that way, we're going to have a counterclockwise. And for some reason, counterclockwise is positive torque. I remember it because to me, it's so weird. I thought clockwise would be positive, but I don't know. Maybe there's a reason out there. I haven't learned it yet. So we say, okay, well, that's positive torque. So we say N2 sine theta times, now this one's just times the distance L. This L comes from the fact that it's just L away from our normal force. It's literally the other end of the ladder. So we now have our definition. So these should equal 0, right? Because our object is not rotating. So it's just equal to 0. So we say, cool beans, bro man dude. Let's go ahead and figure this out. So we just do a little bit of distributing. We go ahead and move our 2 in. So we get mg cosine theta over 2. And then we also we factor the L out. I did a couple of things in one step here. We factor the L out as well, and so we're left with N2 sine theta. This is technically plus, but we moved this one over here because it's weird to have a negative sign on the edge like that. And so we say, okay, really cool beans, bro dude. So we got our L out here. And because our L is out here, we actually can do something special. It's equal to 0, right? So just divide by L, and our L gets annihilated. It just goes away. So actually our length ends up not mattering at all. So our length goes away, and we're left with just the inside. And we say, all right, let's just go ahead and add this part, this mg cosine theta over 2 to the other side, because we want to find N2, right? If we look over here, N2 is the thing we don't have. So we do that. And then we also can divide by sine theta. Now, I'm going to move the 2 underneath the mg, and we can do that because it's multiplication. And then we say cosine theta over sine theta is cotangent theta. So we wind up with this. And from there, we come over here and we say, well, this is N2. We found N2 finally. And it's in terms, we know theta, we know the weight, and 2 is just a number. So we can plug that in, and we find out that m ground is equal to mg2 cotangent theta over mg. And we can simplify actually and multiply by 1 over mg. And we end up canceling the mg's out, and we're left with cotangent theta over 2. And that is what m ground is. If you feel so inclined, you could go ahead, plug in the numbers, and you could figure out m ground just like that. So if you have any questions, let me know. I hope this was pretty clear. I didn't want to rush through anything too crazy. I did expect some knowledge with previous pulley problems and things of that nature. So resolving vectors shouldn't have been an issue. But anyways, that's how these problems work. Subscribe and have a blessed day.